It's 2 minutes to 3 p.m. So I'll wait for around 5 minutes to see if anyone joins. Then I'll get started with today's content. Okay, so it's 3 p.m. already, so I'll get started with today's content soon. Hope few more people join in during this session. Hello and welcome to this week 5 TA session on constraint and unconstrained optimization. So today's agenda could be to discuss the assignment 5 solutions, and I'll be talking about some of the similar problems that you may find in assignment 6, and probably will go through some of the contents that have been covered in the week 6 classes. So I'll get started. Since no one has joined, I'll just get started with solving the assignment 5 questions. I know the solutions will be available to you, but still, let's go through this for the sake of completeness. Okay, so I'll write down the topics that I'll be discussing today. So, first one is the assignment 5 solutions. Next, I'd be intending to discuss probably a little bit about the branch and bound method, if I have time to do so. And then I'll be talking about similar problems to assignment 6 and also transportation problem. Different methods to generate initial basic feasible solution. Okay, yeah, I hope my screen is visible. Looks like it froze in between. Let me wait till it comes up. There's some internet issue, I think. That is why it is lagging. Okay. Yeah, it has come now. So let's start with the assignment 5 solutions. So let me write down the first problem. Yeah, so the first problem tells you to solve this using dual simplex method. So this is max of z equals minus 2x1 minus 3x2 minus x3 subjected to 2x1 plus x2 plus 2x3, which is greater than equals 3. Then you have 3x1 plus 2x2 plus x3 greater than equals 4. And you have the non-negativity constraints of x1, x2, and x3 greater than equals 0. So solve this optimization problem. Solve the above using dual simplex method. Okay, so let me solve this. So as you all know, the first step to solve such problems is to write this problem into the standard form. So let me do that. So the standard form, so this is how we can view it. Yeah, so what you have to do first is that you have to add the slacks that to the two equations, two constraints that are given to you. And as you already know that in dual simplex method, we don't care about the feasibility conditions to begin with, and we just ensure to satisfy the optimality criteria. So you can just add in the first equation, you can just add say x4, and in the next one you can add x5, and or you might subtract, or that thing you can do. But let's see what you can do to solve this. So first you have to convert this into less than equals to type constraint. And this is max of z equals minus 2x1 minus 3x2 minus x3. So there will be some terms added to it, but I'll come to this later. Yeah, first write this in terms of less than equals to constraint. So this will be minus 2x1 minus x2 minus 2x3, and this should be less than equals minus 3. So we'll add one slack and make it equals minus 3. And finally, for the next equation, what you have is minus 3x2, minus 3x1 minus 2x2 minus x3. Then you will be adding this x5, and that should be equals minus 4, right? And your x1, x2, x3, x4, and x5 all are greater than equals 0. And since you have added this x4 and x5 in your constraint, so that should also appear in the objective function with coefficient 0, right? So that's the standard form that you can write. And then your initial basic feasible solution here in this case. So you don't satisfy the feasibility, but that's your starting point. So you can pick x4 equals minus 3 and x5 equals minus 4. And the rest of the variables, you can keep it as 0. And you can some way satisfy the optimality criteria. So let me write down. So the table, the simplex table, but here you can call it as dual simplex table. So this is B, and then you have x1, x2, x3, x4, and x5. The Cj values you can also write down on the top, and the Cj values will be minus 2, minus 3, minus 1, 0, 0. And initially, uh, only x4 and x5 will be in the bases. So you can write down x4 and x5 here. Here you can write it as a4 and a5. And the coefficients corresponding to this are 0. The right hand side are minus 3 and minus 4. And the rest of the things, it's pretty standard that you know. So you can fill this up. So these are the coefficients, right, of the constraints. So I'm filling this up. Now let's see how the Zj minus Cj looks like. So it will be 2, 3, 1, 0, 0. So you're good with the optimality criteria, but your feasibility criteria is not satisfied because x4 and x5 have taken negative values here. So now you can determine which one is the departing variable and which one is the entering variable. So now what you can do first, you have to determine which one is the departing variable, right? So for that, what you can do this min of xbr. So that will be min of, or I should write it as curly brackets xbr, right? So this should be a min of two terms. One would be minus 3 and the other will be minus 4, right? So these are your right hand side and the minimum is minus 4. So you are picking the most negative one. So x5 is the departing variable, right? So this is your departing variable. Okay, so that's great. And the other one is max. So you have to determine now the entering variable. So for that you can take max of 2 divided by minus 3. So it's corresponding to this one and this row which is departing. So first in dual simplex method you are determining which one is the departing variable, unlike the normal simplex method where you have to determine first which one is the entering variable. The next one is 3 divided by minus 2 and the other one is 1 divided by minus 1. So since all are negative coefficients, so that's why you have taken all three here. And the rest is the 0, so you don't care about it. So the maximum of all this will be minus 2 by 3, which corresponds to x1 column. So right, so that means x1 is the entering variable. Okay, so let me write down the second step of this dual simplex table. Okay, so this is CB, this is B, this is XB, then you have B, X1, X2, X3, X4, and X5, right? And you can write down your CJ values as before, which is I think minus 2, minus 3, minus 1, 0, 0. And now what you have is x4 is in the basis, but instead of x5, you have x1 entered here. So this will be a4 and a1, and this will be 0, and this one will be minus 2, right? The right hand side, so now you have to decide the pivot element. So for that, uh, so this goes out, this comes in, this becomes your pivot element and you have to make this one as 1. So you can divide the entire row by minus 3, right? Okay, so if you do that, what you will get is first one is 4 by 3, next one is 1, the next one is I think 2 by 3, Next one is 1 by 3, next one is 0, and the final one is minus 1 by 3. And once you do that, you have to make uh, the corresponding row element of that column to be 0, right? So what you can do, so the transformation that you'll be doing is R1 prime, it's R1, so that's minus 2, uh, plus, or rather it should be minus, right? So let me, minus 2 by 3 times R2, right? So R2 is minus 3, so those get cancelled out and you are minus 3. Yeah, so you are okay. We have one person joining in. Okay, so we have one person joining in. Hi, Shastri. So I'm solving the assignment 5 problems right now. So if you have any questions, you may ask and I'll answer after I solve this problem. Okay, so this is the first problem, and this will be your row transformation, right? So this one you'll be performing to get the corresponding row. Okay, so what happens is that you are making it at 0. For the corresponding B element, what you are left with is minus 3, minus 2 by 3, and you have minus 4 here, right? So this is minus 3 plus 8 by 3. So I think this is minus 1 by 3. So this one is minus 1 by 3, so that's fine. For x2, this is minus 1 and minus 2 by 3 times minus 2. So this is 4 by 3 minus 1, so that's 1 by 3, so that is also fine. The next one you have is minus 2, minus of 2 by 3 times minus 1. So this is 2 by 3 minus 2, so that will be minus 4 by 3. Yeah, so this is also fine. Let me erase this. Yeah, two more calculations to be done here. So that's 1 by 3 times 1 minus. Okay, so this will remain as 1. And the final one is 0 uh, minus 2 by 3 times 1. So this will remain as minus 2 by 3. Okay, so as before, let's see what the optimality criteria looks like. So let me erase this because I have to calculate the reduced cost values here. Okay, so let me write Zj minus Cj, and this will be 0. This will be minus 4 by 3 plus 3, so that should be 5 by 3. Then you have minus 2 by 3 plus 1, so that's 1 by 3. Then this one will be 0, and the last one will be, I think, 2 by 3. Yeah. So before getting into the entering variable, you have to decide on the leaving variable. And it's pretty evident from here that x4 will be the leaving variable because uh, this element, this b element is having a negative value. So what you have here is that x4 is the departing variable. And now you have to check which one should be the entering variable. So for that, as before, what you can do this corresponding to this. So which one is having a negative coefficient that you have to check. So this is 1 by 3 divided by minus 4 by 3, and the last one, it's 2 by 3 divided by minus 2 by 3. And if you do that, so you will get max of uh, minus 1/4 comma minus 1, so that should be minus 1/4. So it will be corresponding to this element, right? And this one is your leaving one. And that means this becomes your pivot. Okay, so in the next step, what you have is, let me write down. So that you can write that x3, I think, is the entering one. Yeah, x3 is the entering variable. Okay, now let's see what you have to do in this step. Okay, so here you can write Cj, and that is, I think, minus 2, minus 3, minus 1, 0, 0. Now you have x3 here as well as x4. This is a3, this is a4. This is minus 1, and this is 0. And you have to first convert this row, right? So you have to multiply it by minus 3/4 to get the transformed row. So what you will be doing is R1 prime is R1 times minus 3/4. Yeah, so once you do that, what you will be left with is 1/4, then it will be 0. Then the next one will be minus 1/4. This one will be 1. This one will be minus 3/4. And the final one will be half, if I'm not wrong. Yeah, half. And now you have to make this element as 0. So for that, the transformation would be, it's R2 prime. So it's 1/3, whatever you had, plus 1/4 times R1. So this will make it as 0. So that's fine. So now that means the first one will be 4/3 plus 1/4 times minus 1/3. So it's 4/3 plus 1/4 times minus 1/3. So this would be 12 and 16. So that's 15 by 12. So that's 5 by 4. Yeah, next one will be 0. Uh, so yeah, R2 is 1. So this should be remaining as 1. So that's fine. Yeah, next one is 2/3 plus 1/4. Okay, let me write down this one. So this is 2/3 plus 1/4 times 1/3. So that will be 8 by 12 plus 1 by 12. So 9 by 12. So that will be 3 by 4. Yeah, next one will be 0. And let's calculate the last two. So that will be one of them will be 1/4 only. Yeah, this one. Yeah, and the final one I have to calculate. So let's do that. So it will be minus 1/3 plus 1/4 times minus 2/3. So this will be minus 1/3 minus 1/6. So that will be minus half. Okay, so let's calculate the reduced cost values. So for the first one, it's -1. So this one will be 1, if I'm not wrong. Let me check again. Oh no, it's this is 0, so this is 2. Yeah, next one will be -1/4 plus 3, so that will be 11, no, -1/4. Yeah, -1/4 plus 3. So that's 12 minus 1. Yeah, that should be 11 by 4. Next one will be 0. Next one will be 3/4. Or I think I've done some mistake. Okay. Yeah, the mistake is this one is -2, right? Let's recalculate this one. So this one will be -2 plus 2. So this is 0. Next one is -1/4 and -6/4. So that's -7 by 4 plus 3. Okay. So let me write down. It's 12. 12 minus 6 minus 1. So there should be 5 by 4, if I'm not wrong. Next one is 0. Next one is 3/4 uh, minus half. So that will be 1/4. Yeah. And the final one will be minus half plus 1. So that will be half. Okay. So now you can notice that you have satisfied your optimality criteria. So all of them are greater than equals 0. And even the feasibility criteria, because this x3 and x4 variables, you have made it as positive. So now the solution that you have obtained is x3 equals 1/4, x4 equals 5 by 4, and the rest of the variables, I think in the original problem you had only 3 variables, x1 and x2, those were zeros, right? Yeah, so the problem asked for the solution, so the answer would be x1 star, x2 star, x3 star. That would be 0, 0, and 1/4, I think. I think we check if there is a mistake on it. Okay, I think this one is x3 and x1, right? Okay, now it should be fine. So this is x1 equals x3 equals 1/4 and x1 equals 5 by 4. So this is 5 by 4. So x2 will be 0, right? And this is 0, this is 1/4. Yeah, so which option had this? I think option B. Yeah, so B is the correct answer. Yeah, so this is how you solve dual simplex problems, and there are a lot of chances of making calculation errors if you do it by hand. So it's better to do this row operations using Excel, so that will be very easy. You just give the formula to Excel and drag it, and the calculations will be done automatically. But I'm not sure if we are allowed to do that in exam. So try it out using calculators only for now. Okay, so that's all about the first problem. So I'll move on to the next ones, but first let me ask Shastri. So if you have any questions, you can ask right now. Okay, looks like no questions from him. Okay, so I'll move on to discussing the other problems. So since the next one is also very similar dual simplex method problem, I won't be solving it. I'll just tell the correct answer. So this problem is giving you this min of z subjected to the constraints 3x1 plus x2 greater than equals 3, 4x1 plus 3x2 greater than equals 6, and x1 plus 2x2 greater than equals 3, x1, x2 greater than equals to 0. So this solve this using dual simplex method as before. So first you have to convert it into the standard form. So let me see if this problem has something which is critical. Yeah, so the min part you can convert it into max, so that's fine. And then the greater than equals to type constraint, you have to convert it into less than equals, and also you have to add the slacks. So again, you'll be starting with some initial basic feasible solution. Sorry, not a feasible solution, initial basic solution, and which is optimal in certain sense. And then it's again determining which variable departs and which one enters. And it's a pretty standard way of finding out. So I think the answer would be this question will be x1 star comma x2 star. So this is 3/5 and 6 by 5. And I think option C would be the correct one here. Okay, so let's look at the third one. So third one has this constraints x1 plus x2 to xn plus say xm equals 0. So this is introduced when what happens is that this optimality criteria is not satisfied. So answer will be A, where this Zj minus Cj is less than 0 for so occurs for some j. So I think that was discussed in the class as well, so that's fine. Fourth problem tells you use the following information to solve the questions. Okay, yeah. So the problem that is given here is max of z equals 2x1 plus 3x2 subjected to x1 plus 2x2 less than equals 7, x1 plus x2 less than equals 4, x1 x2 greater than equals 0. So in order to find the initial dual feasible solution of the optimization problem using dual simplex method, yeah, so how do you reduce it? So that's the problem. So now if you noticed, you can do it using some simplex method because these are less than equals to type constraint, and you can just add x3 and x4 in these two equations, and those x3 and x4 will take values 7 and 4, which is feasible. So initially your solution is feasible. So there is no point of even using dual simplex method here. But if you want to solve it using dual simplex method, you have to do some transformation. So that's all about the problem. So that you can do by so initially what you can do, let's do this actually, this problem. So that this one will be x1 plus 2x2 plus x3, which is 7. This one will be, say, x1 plus x2 plus x4. This is equals 4. And you can write it as 0x3 plus 0x4. So this is your standard form. And then you have x1, x2, x3, and x4 all are greater than equals 0, right? Now, what you can do, this feasibility condition, initially, so x3 and x4 are 7 and 4. So that means what you have to do, you have to introduce something which is x1 plus x2 plus xm equals m. So m is very large. And you can find z1 minus c1. So I think initially, so it will be 0. So this c1 is 2. Okay, so he left, I guess. And this is nothing but 0 minus 3, which is 3. So that means what you can do, that x2 you can replace. So replace x2 by x2 minus m minus x1 minus xm. Now, if you replace this, you will get the modified problem. Max of z equals 2x1 plus 3 n minus x1 minus xm. And the others are 0 anyway, so what you are left with, minus x1 minus 3xm plus 3m subjected to, so it's x1 plus 2x2, x1 plus x3 equals 7. This will give you x1 minus x1 minus 2xm plus x3 equals 7 minus 2m. And finally, you have another equation which is x1 plus x2 equals 4. So this will be uh, xm, and there should be another x4, right? So this should be x4 minus xm equals 4 minus m. And you have another equation which is x1 plus x2 plus x4, sorry, xm equals m. So now the transform problem will be max of minus x1 minus 3xm plus 3m. So that is there in all of the objectives, all of the options. Next would be minus x1 um, minus 2xm. Okay, so that's there in B and D, and plus xp, right? Equals 7 minus 2m. So B and D could be potential answers. And the final one is x4 minus xm equals 4 minus m. So that's there in D, not in B. So D will be the correct answer, right? The answer is D. Okay, so that's all about the fourth one. So now you are asked to solve the optimization problem using dual simplex method. And again, I'm not going to solve it anyway because you can do it using the similar method, or you can use Excel to solve it. So what you have here is that this problem 5. So when you are asked to solve it, you can even do it in graphical method if you want. So in this problem, I think the solution would be x1 star and x2 star equals 1 and 3. So this is 1 and 3. And in that case, you'll be left with a z star value of 11. Okay, so z star is 11. So same method using dual simplex method. So your answer will be here is A and C. Okay, so let's move on to the sixth problem. Which of the following is true for Gomory's method? So first one is saying Gomory's constraint variable is introduced before obtaining the optimal solution by simplex method. That's not true. Gomory's constraint or variable is introduced after obtaining the optimal solution by simplex method. So that's true. Uh, Third, C is not true and D is not true. So this is again discussed in the class, I think. So this is related to the Gomory's cutting plane method, right? For integer programs. It's introduced after obtaining optimal solution by simplex method. And then you have to resolve it again, right? After introducing that cut. Okay. The seventh problem asks you to solve a integer programming problem where you have to use Gomory's cutting plane method. So let me do this because since I haven't discussed this Gomory's cutting plane method in the class, but let me not solve the LPs. I'll directly write the LPs solution, but let me show you the procedure to solve it. So this is max of z equals 7x1 plus 9x2 subjected to minus x1 plus 3x2 less than equals 6, 7x1 plus x2 less than equals 35, x1 and x2 are positive and also they are integers. So that's the extra condition that you have. Okay, so solve this integer program by Gomory's cutting plane method. Okay, so let's do this. So here what you have is first you're given this problem. But the first step will be you ignore that these are integer variables and you solve an LP. And after you solve that LP, so you'll try to add a cut so that that solution gets violated, right? So that's the procedure, and then you try to move as close as possible to the convex hull of the problem. Okay, so or the convex hull of the feasible region. That should be called like that, right? Okay, so here, when you solve this problem, one way of doing it is that you can add Gomory's cut based on the variables or the simplex tableau row that you have got, and after that you can proceed. So let me do this. Okay, so let me actually do this so I'll be able to understand. So first it's converting into the standard form. Okay, so that would be max of z equals 7x1 plus 9x2 plus 0x3 plus 0x4. And let's not bother about the integer variables just now. So this should be plus x3 equals 6. And this 7x1 plus x2 plus x4, this is equals 35. And you can write x1, x2, x3, and x4 all are greater than equals 0. So here, what you can do, uh, let's uh, let's do that. So again, you can use simplex method since the right hand side are positive anyway. And to begin with, you can construct this tableau. So you are familiar with this. So you can write CJ here. This is 7, this is 9, this is 0, this is 0. This is nothing but 0 and 0. This is A3 and A4. This is X3 and X4. This is 6 and 35. And you can write minus 1, 3, 1, 0, 7, 1, 0, 1. These are your reduced costs. So this will be minus 7, minus 9, 0, 0. Most negative is this one. So this is entering. Calculate the min ratio. So this is 2. This is 35 by 1. So that's 35. I don't know why it is written like something else. But anyway, this is the leaving variable. Okay, so in the next step, what you have is mostly similar things. So first you have to construct this table again. Now this one will be your pivot and x2 will enter into the basis. This is A2, A4, and let me write down the CJ values. And this one will be 9. This one will be 0. Yeah, the first row you can divide it by 3, so you'll be left with 2 minus 1/3, 1, 1/3, 0. And the next one you can just subtract this transformed one. So that will be 33. That will be 22 by 3. This one will be 0 as is expected, minus 1/3 and 1. So as before, do the similar exercise. So this one will be minus 10. Next one will be 0. Next one will be 3. And the last one will be 0. So this one will be your entering one. And which one will be your leaving one? So that will be that you have to calculate. So the first one is anyway negative, so that's not of any use. This one, so this is 3 by 22, right? So anyway, this will be your leaving variable, and this will be your pivot. So in the next step, what you will be left with is CB, B, XB, again B, X1, X2, X3, X4. Now, what you have to do, you have to multiply that row by 3 by 22. So once you do that, so let me write down, this will be X2, this will be X1, this will be A2, this will be A1, and let me write down the CJ values. This is 7900. This one will be 9. This one will be 7. And now multiply. So that will be 99 by 22. So that will be 9 by 2. Next one will be 1. Next one will be 0. Next it will be minus 1 by 22. And finally it will be 3 by 22. And now uh, what you can do, you can divide this row by 22 and add it up to the first one. So that will be 2 plus 3 by 2. So that's 7 by 2. This one will be 0. There's 1. So that will remain as 1. Next one will be 1 by 22. We have to add it up, right? So it's 1/3 minus 1 by 66. So that's 21 by 66 if I'm not wrong. Uh, Yeah, 21 by 66 is nothing but 7 by 22. Finally, it's 0 plus 1 by 22, so that's 1 by 22. Okay, so that's great. And then finally, you have to get the reduced cost value. So this will be 0, this will be 0, this will be 63 by 22, so that, uh, yeah, 63 by 22 minus 7 by 22, so that's 56 by 22, which is 28 by 11. And finally, it's 9 by 22 plus 21 by 22, so that's 30 by 22, which is 15 by 11. So all of them are greater than equals 0, so you have reached optimality. So for this solution will be, so this is, if you solve it as an LP, you get x1 equals 9 by 2 and x2 equals 7 by 2. And everything else, the slacks that you have added, those will be 0, right? But this is not the solution to the integer programming problem. So for that, what you have to do, you have to add a cut so that this solution gets violated. So it's like you are eliminating, uh, like what you can say is that you are eliminating this solution or you are chopping off the solution. So that's one corner point that you are kind of taking care of. Okay, so Let me just do one more step in this problem because the rest of it will be standard. So what you can do, so the Gomory skirt you can add corresponding to say x2. Now, if you notice, this equation will be, so the first equation, you can think of it as x7 by 2 equals x2 plus 7 by 22 x3 plus 1 by 22 x4, right? So this you can think of. So you can also write it as minus 7 by 22 x3 minus 1 by 22 x4 uh, equals x2 minus 7 by 2, right? But actually, uh, what happens is that your x2 is not 7 by 2. So what you can also do, mm, so you can take the fractional part of the right hand side. Okay, um, and also the left hand side. So the fractional part in the left hand side remains as minus 7 by 22 x3 and minus 1 by 22 x4. And in the right hand side, what you can have is half as the like the fractional part. So Gomory's cut for x2 rho will be minus 7 by 22 x3 minus 1 by 22 x4 plus s1 equals half, right? Or it should be, I think, minus half. Yeah, so it will be, yeah, because if you take the floor, I think you will be left with, yeah. So the fractional part is half and there is a minus sign on top of it. Okay, so this you can add as the cut, and the previous solution will violate it because in the previous solution what you had x3 and x4 to be zeros, and now what you are making is s1 as minus half. Yeah, so in that case, so this is just another equation. Let me explain it in a better way. So let me just check one thing. Okay, so yeah, so I'll just check one thing how to write this. Connecting plane method thing. Okay, so what you can do in general, I think you can write it as W transpose. X. Okay, so yeah, one way of doing it is, so this is Gomory skirt. Another method could be to write it as J belongs to N. This is B inverse N IJ minus B inverse N Ij. So this was not discussed in the class, but this is one method I found useful. And this is greater than equals B inverse B I minus this B inverse B. So for this, you need to know this B inverse. So the basis you already know, and the inverses you can calculate. But yeah, the good thing about it is that your basis is generally an identity. So when you do it for x2, I think what happens is that you're left with small b minus b, so that's 7 by 2 minus 3, so that's half. And the other portion, this j belongs to n, so this is x2 variable, and this is this equation. So the x2 automatically vanishes because that's 1 minus 1, and the 7 by 22 minus 0, 1 by 22, 0. Yeah, so if you apply this, what you get is that 7 by 22 x3 plus 1 by 22 x4, it's greater than equals half. That means you can write minus 7 by 22 x3 minus 1 by 22 x4, which is less than equals minus half. And that's why you can also write minus 7 by 22. So you can add a slack here and you can make it as minus half. So this is the one that I have got before. So this is exactly fine. So the good thing is about B inverse is identity here once you transform it. And the N and J, those things you can pick correspondingly. Okay, so that was all about this method. Uh, so that's the first cut that you add. Now what you have to do, you have to, using this cut, you have to solve the LP again. So now it will be some 3 rows or something that you will be getting. The next cut that you will be again adding will be, so the next cut will be, I think, minus 4 by 7 equals minus 1 by 7 x4 minus 6 by 7 s1, and then because of that inequality sign, you have to introduce a slack. Again, if you solve the simplex method, keep on solving it. Finally, what you will obtain, sorry about that, x1 star equals 4, x2 star equals 3, and that will be your uh, optimality. And since you have got to an integer point, and your z star will be 7 times 4, 28, plus 9 by 3, 9 times 3, 27. So it's 55. So let's see which option is correct. So the answer will be option A, right? So this is x1 star, x2 star equals 4 by 3. Okay, so let's solve one more. So I haven't shown you the next steps. So the LPs you have to keep on solving. And you can also solve it using Excel's, so not a problem. So it's just one more equation that you add, and that you have to take that constraint into account, and you keep on solving your LP. So that's the idea of Gomory's cutting plane. Okay, so the eighth problem is maximizing z equals 8x1 plus 5x2 subjected to the constraint 9x1 plus 5x2 less than equals 45, x1 plus x2 less than equals 6, x1 x2 greater than equals 0, and finally what you have is x1 x2 are integer. Okay, so now solve this using the branch and bound method. So that is another interesting method that you can apply. Okay, so let's try to solve this. So in this problem, what you have to do, so you know the concept of, say, branching. So first you don't care about the integer variable and you solve the problem as it is. So that's LP1. So this is first step. So you'll get x1 star equals 3.75 and x2 star equals 2.25. Now you have two options of like branching. So let's branch with respect to x1 variable. So now if you branch, it could be x1 less than equals 3, or you have x1 greater than equals 4. So that's subproblem 1. So this subproblem 1, if you solve it using LP again, you'll be left with x1 and x2 star equals 3 and 3. And from the other portion, you will be left with x1 star, x2 star equals 4 and 1.8. So you can again branch based on this one. So one of the branches will be x2 less than equals 1, and the other will be x2 greater than equals 2. So this is subproblem 2. So the subproblem 3, if you solve using LP, what you will be getting is x1 star, x2 star equals 4.44 and 1. And from this one, subproblem 4, if you solve it, you'll get x1 star, x2 star equals uh, okay, so this gives no feasible solution. So if you put x2 greater than equals 2, so there is no feasible solution because uh, your x1 is now 4, right? So that's why the issue is. So it's minimum 4, and yeah, so you have two contradictory equations, so there's no feasible solution. And finally, what you can do, you have to again branch based on this. So that's x1 less than equals 4 and x1 greater than equals 5. So this is subproblem 5. So this gives you x1 star, x2 star. So this is equals 4 comma 1, and this one is p6, gives you x1 star, x2 star. This is 5 comma 0. And the objective here is 8x1 plus 5x2. So this is z star is 37. Here z star is 40. And I think you got one more integer point which is here, 3. So that will be 8 plus 5. So that will be 39, right? So out of all those things, this 40 is the maximum one, right? So the optimal solution. So here I think there were two options which is correct. So answer is B and D. So B tells you that x1 star, x2 star is 5 and 0, and D is Z star, which is 40. Okay, so let's move on to problem 9. So this is the instruction. So the maximization of, let me write down the problem. Max of Z equals x1 plus x2, and this is subjected to 2x1 plus 5x2 less than equals 16, 6x1 plus 5x2 less than equals 30, x1, x2 greater than equals 0, x1 is integer, but x2 can be anything, right? So the answer will be, this is a mixed integer problem. So that's a mixed integer programming problem. So that's pretty straightforward. And finally, what you have is the 10th problem. You have to solve this, right? So you can again solve it using some branch and bound technique and so on. And the optimization problem, the solution now, it's pretty simple, right? You know x1 is an integer. So you know that A and B options will not be correct. So now you're left with two options, C and D. So for C, let's check the feasibility condition. So that's 2 times. So it's solving through the options. You don't even need to solve the problem. It's so simple. So it's nothing but 9 plus 6, which is 15. So this is satisfied. This is 6 times 3 plus 5 times 9 by 5. So that will be 18 plus 9. So that's 27. This is also satisfied. For this one, z is x1 plus x2, which is this is nothing but 24 by 5. So for option C, right? For option D, let's check the feasibility criteria. So that's 2 times 4 plus 5 times 6 by 5. So that's 8 plus 6, 14. This is nothing but again 6 times 4 plus 5 times 6 by 5. So that's 24 plus 6, which is 30. So this is also fine. For this, that is x1 plus x2, which is 26 by 5. So this one is greater, right? Since this is a maximization problem, and the answer will be D. Okay, so that's one trick that you can use to solve this problem. Okay, and if you want to go in the conventional way for this problem, you can again solve using the simplex tableau, and you can again add Gomory's constraint or the Gomory's cutting plane. And based on that, you keep on solving and you'll get the solution, or even you can use branch and bound technique. But while solving the LP, it's very easy if you can feed it to a solver like Excel or maybe some other programming languages, Python and so on. So it's not required that you are solving this by hand using the simplex method. So it's just determining the for Gomory's cutting plane, it's determining the basis and non-basis matrix and the right-hand side and so on. Okay, so that's all about assignment 5 discussion. And next, what I wanted to do, I think, little bit about branch and bound method, but I think I've already covered it in this content. So, okay, this is there is some issue, I think. My mouse pointer is not moving. Okay, I'm unable to edit it for some reason. It's not editing. Just a minute, come back. Yeah, now it's okay. Yeah, so what I intended to do is okay, so this is oh, I erased it. Okay, so this is okay, so this is done. Branch and bound method is done. So let's move on to the similar problems that you'll find in assignment 6, and let's try to do that. Okay, so let me give the heading here. Similar problems to assignment 6. Yeah, I'll discuss the solution in detail in the next class because this is due, I think, this Wednesday. And once you solve it, then I'll start discussing. Okay, let me have some water and start. Yeah, so the topic of discussion mainly in week 6 content is transportation problem, right? So it's a very simple concept where these are your origin. So suppose you have 1 to m origins, and then you have certain destinations, which you can name it as 1, 2, up until n. So it's how much quantity that you will be moving from one origin to the other destinations. So this is x11, x12, and so on. This is x1n. This is xm1, and this is xmn. So these are your decision variables. So as you can see, or you can guess how many decision variables you can have a guess. And that was one of the problems, I think. And the other could be how many equality constraints you have, right? So you will have the summations, and you, so these are your row sums, and you'll also have some column sums. So that should add up to certain values. So for every column, you will have a equality constraint, and for every row, you will have an equality constraint, right? So you can, I think, get how many equality constraints you can have from this problem. And there is this concept of balanced transportation problem. So if the right-hand sides of this, or the amount, the quantities that are you are transferring from all the origins, if you add it up, and the quantity you are delivering to all the destinations, if you add it up as well, so that if that is equal, that means this is a balanced problem. In case of an unbalanced problem, what we typically do is that we convert it into a balanced problem by using some extra equation, and by adding those variables that you extra variables that you add with a zero coefficient in the objective function. So the constraints are kind of clear. The objective here is summation I belongs to the origin, j belongs to the destination, and this transfers have certain costs. So those are Cij times Xij, right? So this is your objective function. So that's all about this transportation problem. Now, uh, you know that you can make it, or rather you can express it in terms of certain, what do you call it, in terms of a table. So let's express this. So this is transportation problem. So let's first I'll ask you find the cost of initial BFS by row minima method. So that's the first method that I'll be talking about. Now, let me give you this table. So this is origin 1, 2, 3. This numbers is, let's say it's 38, 60, 100. So these are your cost, 20, say 140, 60, 80, 120. And then you have 80, 16, 140, 40. These are your row sums AI, uh, and then you have your column sums BJ, or it's not the row sums or column sums, it's the amount of uh, goods you need to transfer, or that's already present in that location, right? So let's say it's 14, this is 18, this is 36, and this is, say, it's 10, 16, 14, and 28. So let's add it up. So I think this should be I and this should be BJ. And yeah, here it should be I and here it should be J. Okay, so if you add it up, you get 68 for this one, And for this one also, you get 68. So this is a balanced transportation problem. So that's fine. So you need not convert anything in this problem. So now let's solve it using row minima method. So what kind of allocations that you need to make, that you have to determine. Okay, so in the row minima method, yeah, so let me give this heading. So let me draw this table again. So it's a 3 by 4 table, right? So you have four destinations. So I've written it like this. Okay, D1, D2, D3, D4. Okay, so let me create this. Okay, I have created one table. So this is origin 1, 2, 3, destination 1, 2, 3, 4. And the cost I can write 38, 60, 100, 20, 140, 60, 80, 120. Then you have 10, 16, 14, 28. Yeah, so the row minima method, and also I can write down these things like 14, 18, 36, 10. Okay, so I think I've written this wrong. So this one will be 80, 16, 140, and 40. Yeah, this one is 10, 16, 14, and 28. Okay, so now it's perfect. Now what I have to do, it's the row minima method. So let me write the allocations using a different color, say red. So what you can do, in the first row, the minimum one is 20, right? That's the cost, which is minimum. And the one that maximum that you can allocate there is minimum of 14 and 28. So let's allocate 14 here. So that means next what you can do in the row 1 or the origin 1, you cannot allocate anything else. So let's delete that row and you'll be left with the second last two rows, right? So let's do this. So what you are left with, so something like 140, 60, 80, 120, 80, 16, 140, 40. Here it should be 18, this is 36, this is 10, 16, 14, and now you have already allocated 14 here, so you're left with 14. So these are your D1, D2, D3, D4, origin 2, and origin 3. Now let's see what will be the allocation here. So if you notice again in this next row, 60 is the minimum one, and you can allocate minimum of 16 and 18, which is 16. So let's allocate 16 here. Okay, so that's great. And what you can do uh, in that row again, you can allocate two more as well, but and you can delete the column because you have already allocated there. So let's move on to the next table, which is, see, this will have O2, O3, D1. So now you can delete D2. So this is D3, this is D4. Let's write down the cost, 140, 80, 120, 80, 140, 140. Let's adjust this. So this will be 2, this is 36, this is 10, this is 14, this is 14. Okay, so again the row minima method, 80 is the minimum one. So you can allocate 2 there. So you can now delete the entire this origin 2 row, and you'll be left with only one row now. Okay, so this is 80, 140, and 40. This is 36, this is 10, this is 12, this is 14. Now it's allocating this something here. So 80 is the minimum one. You can allocate 10 here, right? So that's another step. Oh no, sorry. I think 40 is the minimum one here. So first you have to allocate 14 here. So you can allocate 14. This is O3. This is D1, D3, D4. Okay, so the next step, you can delete D4. So it's D1, D3, O3. So this is 80, 140. So 22 is remaining here, and here it's 10 and 12. What you can do, again, let me put the allocation. So it will be 10 being allocated here. And finally, what you'll be left with is, now you can delete that column, and let me draw the final one. So this is D3, this is O3, this is 140, this is 12, this is 12, and it's just you have to give 12 here. So let's write down the allocations. So the allocations will look like, so I'll just write down the allocations. So here it's 14. O2 D2 is 16. So let me name this first. Okay. O2 D2 is 16. Next is O2 D3, which is 2. Then it's O3 D4, which is 14. O3 D1 is 10. O3 D3 is 12. Let's see if the summations are fine. This is 14, 18. 14 plus 12, 26. This is 36. So that's fine. Here that's 10, 16, 14, 28. So this is also fine. So you have already satisfied your constraints. Now we can calculate the cost. Now the cost will be, so it's just multiplying with the corresponding cost. So it's 20 times 14 plus 60 times 16 plus 80 times 2 plus 80 times 10 plus 140 times 12 plus 40 times 14. So this will be your cost. So let's see. This is 280 plus 960 plus 160 plus 800 plus 1680 plus 560, right? So if you calculate it, it will be 28 plus 96, so that's 124, 140, 220, 388 plus 56, 394, 4. Yeah, so this will be your correct answer. So that you can get using your row minima method. Okay, so let's do next problem. Let's move on to the next one. So let's solve this. Okay. Say, so let's solve this above problem using column minima method. So the problem will be find the cost of by column minima method. Okay, so it's again very similar. Uh, so let me write down the first table itself, right? Oh, network is lost. Yeah, the network went out for a brief amount of time, I think. Let me see if it's recording or not. It's getting recorded. Okay, so let me solve this one. So find the cost of initial VFS by column minima method, and let me write down the costs just before. Plus 38, 60, 100, 20. So hope I'm writing it correctly. Yeah. Then it's 140, 60, 80, 120, and it's 80, 16, 140, and 40, right? This is 14, 18, 36. This is 10, 16, 14, 28. Now, for the column minima method, what you have to do, you have to pick, say, the first column and check which one is having the lower value, right? So let's solve this. Okay, so let me write down this answer. So this is column minima method. Yeah, so first of all, what you have to do, you have to check where you can do allocation. So I'll do it quickly. So here it will be 10, right? So you can name it as 1 over 2 over 3, D1, D2, D3, D4. Yeah, the next table, what you can do, you can delete the first column. So you'll be left with 3 columns. This is a 1 or 2 or 3, D2, D3, D4. And you can write down the cost as well. So I'm not writing down the cost, but the one which is having the minimum value in this is 16, right? So here, what you can do, so minimum of 16 and 36, you can allot 16 here. Okay, let me write down the cost for the sake of completeness, because there would be confusions later. So initially, so this was 16, 14, 28. So here it is 4, 18, and 36. Now we can check this 16 you can allocate, and you can delete that column again. So what you are left with is now two columns and three rows. This is D3, D4. This is O1, O2, O3. This is 100, 20, 80, 20, 120, 140, 40. So this is 14, 28. This is 4, 18, 20. Right. Okay, so next what you can do, where there is this 80 thing written, so here you can allocate 14, and you can delete that column again. So what you're left with now is just a single column, three rows. So 1, 2, 3, D4. So this is 120, 120, 40. This is 28. This is 4, 4, D. So again, you can allocate, the minimum one is 20, so you can allocate 4 here, and then that will be deleted, that row. After that, you can allocate 20 here, and finally you can allocate 4 here, right? It's pretty simple. So I'm not showing you the rest of the details. So this is allocation. So here it's 10. Next is here it is 16. Not here. So O3 D2, this is 16. O2 D3, so this is 14. And O1 D4, so this is 4. This is 4. This is 20. So now if you add it up, this is 14, 18, 36, 10, 16, 14, and 28. So this is a valid allocation. And let's calculate the cost. So it's 10 times 38 plus 4 times 20 plus 14 times 80 plus 4 times 120 plus 16 times 16 plus 20 times 40. So this is 380 plus 80 plus 1120 plus 480 plus 256. Oh, sorry. Plus 800. So this is nothing but 46, 58, 66, 206, 860 plus 256, 6, 1. No, I think I made a mistake. Okay, so this is, let me check if it's correct or not. Okay, I think this is correct. So now you can notice by this column minima method, you have allocated, and so you are trying to minimize this in your transportation problem, right? So that means in the row minima, the initial allocation was not at all optimal. It was giving you a cost of 4440, and here you are getting somewhat better, 3116. But it might happen that this is also not the optimal one. So to find the optimality, probably I'll show it in the next class because I'll run out of time today. And anyway, you'll be solving the assignment. After that, we can discuss this. Okay, so let's solve one or two more method. So I think Vogel's approximation method also I think we can discuss in the next class, and also the optimality criterias and how do you check it and how do you solve it, those things, the UV method, and also the job scheduling problem part. So I think those I'll be discussing in the next lecture. And from next week, I think MEMS part will start with the nonlinear uh, probably optimization portion. So yeah, I'll probably talking about it in the later in the next class briefly as well. So let's solve two more problems. One using northwest corner method, another is the matrix minimum method. And then I'll wrap it up for today. So let's write down the third problem. Okay, so it will be, so again, I'll give you one transportation problem. So to find the cost of initial basic feasible solution by northwest corner method. Okay, so let's try to keep the numbers as simple this time. Let me see how much of it is possible. Okay, so let's name it as 1023, D1, D2, D3, D4. These are your AI, these are your PJs. This is 6 to 14, 8. This 4, 12, 10, 18. This is 16, 6, 6 and 4. These are your 500, 700, 800. This is your 400, 600, 700, 300. So if you add it up, everything will add up to 2000. So this is again a balanced problem. Okay, so let's solve this. Yeah, I have some 10 minutes remaining, so I'll try to quickly solve it, and then if there is time, I'll go into the matrix minimum method. Okay, so in this method, what you have to do, let's write down this first. 6 to 14, 8. So these are my cost. Okay, so now northwest corner is this one. So you have to start from here. And now you can notice that you can allocate 400 here. And once you do it, the first one, you can again allocate 100. So this will be 100. Then again you will can allocate 100 here. So this will become 0. Then in the next row, what you can do is, so I'm not drawing it again and again. So that means you are deleting the first row after this. In the second row, what you can do, once you have allocated 100 here, so this becomes 0. This becomes 500. So again, what you can do here, you can do 500. Then this becomes 200. This becomes 0. And you can delete this column again and you'll be left with something reduced. But even before that, you can allocate your 200 here. This becomes 0. Finally, this becomes your 500. Sorry. Now you can delete your second row as well. So you are left with only two choices. So here you can allocate 500 and here you can allocate 300. So it's just starting from the northwest end and just keep moving on the east side and then the south. Okay, so this becomes 0, this becomes 0, this becomes 300 first and then becomes 0. So the allocations will look like 400, 100, 500, 200, this is 500 and 300. And let's find out the cost. So cost is 6 times 400 plus 2 times 100 plus uh, this is 12 times 500, 10 times 200, 6 times 500 plus 4 times 300. So this is 26 and 60, that's 86 plus 2106 plus 3136 plus, well, 14, so this is 14800. Yeah, so that will be your answer. So this is fine. So this is by northwest corner method. And finally, the last method that I wanted to discuss today is the matrix minima method. So let's solve the same problem again. Let me write down the problem. Okay, so find the cost of initial BFS by matrix minima method. So as before, what I can do, I can draw the initial matrix. This is 6, 2, 14, 8. Then you have 4, 12, 10, 18. 16, 6, 6, 4. And these are your 500, 700, 800. This is 400, 600, 700, 300. So this is O1, O2, O3, D1, D2, D3, D4. Yeah, so overall, which one is the minimum in this matrix? First, you have to find. Okay, I'll solve this. So, for this one, what you have to do first is find out the overall minima, right? So, here it's 2, which is the overall minima in this problem. And let's see how much we can allocate. So, actually, 500 can be allocated here. So, this becomes 0. This becomes 100. So you can delete the first row. So after that, which is the minimum? So 4 is the minimum one. And there are two locations where this occurs, but you can pick the first one according to the row, say. So it's 400 and 700, minimum of that two. So you can allocate 400 here. So this becomes 0, this becomes 300. And you can delete the first column in that case. After that, what you are left with, again, 4 will be the minimum one, and you can allocate 300 there. So this becomes 0, this becomes 500. So you can again delete the last column. So you're left with this thing, this portion. So there 6 is the minimum one. And in that case, what you can allocate in the first one, the left one, you can allocate minimum of 100 and 500. So 100 goes here. So this becomes 0. You can delete that column as well. And then you're left with the 10 and 6. And so this becomes 400. So 300 goes here and 400 goes here. Okay, so that's a simple way of doing it. So this is using matrix minima, and these are your allocations. Yeah, so if you add it up, it's 500, 700, 800, and then 400, 600. Yeah, so the allocations are perfect here. And now the cost you can calculate. So this is 2 times 500 plus 4 times 400, 10 times 300, 6 times 100, plus 6 times 400, plus 4 times 300. So this is 10 plus 16, 26, 6 plus 13, that's 56, 662, 2 plus 24, that's 86, plus 12, 98. Okay, so it's 9800. Yeah, so this is the answer for this one. So in the other method, we got a cost which is higher than this one, and so that means this could be a better starting point using this matrix minima method, but it might happen that you'll need certain steps which is probably equal or more than that you got in the previous method. So the optimality thing we'll see in the next class, since I've run out of time. And yeah, the optimality thing will come. And before that, even Vogel's approximate method uh, will show you another way of generating initial basic feasible solution. And from that point onwards, you can use a certain technique which has some similarities with the dual variable, or rather it's directly related to that, so you can derive it, and I think that was shown in the class, and Based on that, you have some certain criteria, and you can have those optimality criteria implemented in a simple way and solve those problems to optimality, right? And then there is discussions on non-degeneracy and those things and degenerate problems. So I think, yeah, those I'll discuss in the next one. And then there is this job scheduling problem where the row and column sums or the AI and VJ values are one everywhere. So that's the basic difference. So it's just allocating only one job to one person. And that's the idea of those problems. So I think uh, that is again a balanced transportation problem. And if there is some unbalanced problem, how to convert it into the balanced problem. So that will also be discussed in the next class. So with that, this first portion of linear programming will come to an end. So its search portion will come to an end, and MAM's portions will begin. So it's already around 5 p.m. now, and it's almost more than 2 hours that I'm teaching. So I'll stop for today. And yeah, since no one is here, I'll stop the recording and the session. Hope you'll go through it later. And if you have any doubts, you can always reach out to me uh, through the discussion forum. So hopefully, yeah, people will join in next week, or probably they'll post doubts, and yeah, I'll answer it happily. Okay, so thank you everyone.